supply is low. So resistors in parallel. As shown in the diagram, there are three resistors R1, R2 and R3. They are connected in parallel. Okay, and the terminals are C and D, through which there is a diversion for the parallel connection. So we can observe, so here by the common sense we can understand that the potential difference across C and D would be same. Okay, for all three resistors. But current is different. The current flowing through R1, through R2 and R3 would be different, and hence we write the equation that is I is the net current across the circuit is equal to I1 plus I2 plus I3. So using Ohm's law, we get that I1 equal to V upon R1, I2 equal to V upon R2, I3 equal to V upon R3. And for net parallel resistance, we have I equal to V upon Rp. Therefore, finally we are getting the equation by reducing, and we are getting the equation that 1 upon Rp equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Okay. So, if the resistors are connected in parallel, then the sum of reciprocals of the individual resistance is equal to the reciprocal of equivalent resistance. The current in various resistors are inversely proportional to the resistances. However, the total current is the sum of the currents flowing in the different branches. The voltage across each resistor is same. The effective resistance of the combination is less than that of individual resistance in the combination. The combination is used to decrease resistance in a circuit. Advantages of parallel circuits in domestic wirings. The arrangement of lights and various other electrical appliances in parallel circuits is used in domestic wiring because of following advantages. In parallel circuits, if one electrical appliance stops working due to some defect, then all other appliances keep working normally. For example, if a number of bulbs are connected in parallel circuits and one bulb gets fused, then all the remaining bulbs will keep glowing. Second, in parallel circuits, each electrical appliance has its own switch, due to which it can be turned on or off independently without affecting other appliances. For example, all the bulbs joined in parallel circuits in a house have separate switches, due to which we can switch on or off any bulb as required without affecting other bulbs in the house. In parallel circuits, third point, in parallel circuits, each electrical appliance gets the same voltage as that of power supply line. Due to this, all the appliances will work properly. For example, all the bulbs connected in parallel circuits gets the same voltage of 220 volts of power supply line and hence glow very brightly. Fourth point, in the parallel connection of electrical appliances, the overall resistance of the household circuit is reduced, due to which the current from the power supply is high. That is, every appliance can therefore draw the required amount of current. For example, in parallel circuits, even the high power rating appliances like electric irons, water heaters and air conditioners can draw the high current needed for their proper functioning. Let us find what is Joule's law. Let V be the potential difference across applied between two terminals of a conductor of resistance R. Then by Ohm's law, obviously we can write V upon R equal to I. So if current I is passing through the conductor for time t, then Q is equal to IT. We have already discussed this. Potential difference is the work done, that is actually work done during flow of charge. So V equal to W by Q, therefore W equal to V into Q. So from the above relation we can substitute V equal to IR, we can substitute for Q which is equal to IT. So we are getting W equal to IR into IT, that is I square RT, but IR equal to V, therefore W equal to VIT. So we'll be getting various expressions now, various other expressions for work, for heat solve. So you'll have to just remember. So when current flows through a conductor, the work done I square RT is converted into heat, that is W equal to I square RT joule. Usually we express heat energy into calories. So the relation between joule and calorie is 4.18 joule is 1 calorie. Hence, heat produced in a conductor in terms of calories is given by H equal to, that is heat, equal to I square RT upon 4.18 in terms of calories. Else it would have been I square RT joules. So Joule's law now we can have the definition, actual definition of Joule's law. So Joule's law can be stated as the quantity of heat generated in a conductor of resistance when a current flowing through it for a time t is directly proportional to first square of the current, second the resistance of the conductor, and third the time for which the current flows. So using Ohm's law, we can rewrite the Joule's law as H equal to I square RT upon 4.18 calories, which is equal to V square T upon 4.18 R calories, and which will also be equal to VIT upon 4.18 calories. So what we can understand by the term electric power? Power is the rate of doing work. Similarly, electric power is the electric work done per unit time. Therefore, electric power is also defined as the rate at which electrical energy is consumed. The SI unit of electric power is watt. So 1 watt power is defined as if 1 joule of work is done per second, then the electric power is 1 watt. That is 1 watt equal to 1 joule upon 1 second. Now kilowatt is the unit which is used for commercial purpose, and hence 1 kilowatt equal to 1000 watt. Now formula for calculating electric power. We know that power is work done per unit time, but W is VIT joules from Joule's law. So P equal to VIT upon T, therefore P equal to VI. This is a very important relation, P equal to V into I. Thus, we get electric power equal to voltage into current. So using Ohm's law, we can get P equal to VI, that is equal to I square R, that is equal to V square by R. So P equal to V into I, which is equal to I square R, which is equal to V square upon R. So joule per second is watt, as we know. So the commercial unit of electric energy is kilowatt, kilowatt hour actually, commonly known as unit. That is 1 unit equal to 1 kilowatt hour. So conversion, 1 kilowatt hour equal to 1000 watt, and 1 hour is converted into second as into 3600 seconds. So we get 1 kilowatt hour equal to 3.6 into 10 to the power 6 joules. Heating effect of electric current. When current flows through a metallic conductor, the free electrons in the metal start moving from the end which is at lower potential. These moving free electrons collide with the atoms of the metal. At each collision, a part of kinetic energy of electron converts into heat, and slowly the temperature of the conductor begins to rise. Thus, the production of heat energy in a conductor by the electric current flowing through it is called the heating effect of the current. A given current will produce more heat per unit time if the two resistances are connected in series than when they are connected in parallel. It should be noted that all the appliances which run on electricity do not convert all the electric energy into heat energy. So only the electrical heating appliances convert most of the electric energy into heat energy. For example, when electric current is passed through an electric appliances such as fan, then most of the electric energy is used up in running the fan or turning the fan. Only a very small amount of electric energy is converted into heat energy by a fan. So due to this, an electric fan becomes slightly warm when run continuously for a long time. Applications of heating effect of electric current. In an electric circuit, the unavoidable heating can increase the temperature of the components and also alter their properties. However, heating effect of electric current has many useful applications. The most common examples are electric iron, electric toaster, electric oven, electric kettle, and electric heater. An electric bulb consists of a filament. This filament becomes hot and emits light. It is made up of a metal with high melting point such as tungsten, whose melting point is 3380 degrees centigrade. The bulbs are usually filled with chemically inactive nitrogen and argon, which prevents their oxidation. So these gases, they are filled to prolong the life of filament. An electric iron consists of a coil of high resistance covered by mica sheets and kept inside the heavy metal block. When electric current passes through the coil, it gets heated and can be used for ironing clothes. The mica sheet is a bad conductor of electricity and good conductor of heat. It prevents the current from entering into the metal and thus protecting the user from getting an electric shock. An important application of heating effect is the fuse used in electric circuits. It protects circuits and appliances by stopping the flow of any excess electric current. The fuse is placed in series with the device. It consists of a piece of wire made of an alloy of low melting point, for example lead and tin. If a current larger than the specified value flows through the circuit, the temperature of fuse wire increases. This melts the fuse wire and breaks the circuit. The fuse wire is usually enclosed in a cartridge of porcelain or similar material with metal ends. In industry, soldering, welding, cutting, drilling, and working of electric furnaces are based on heating effect of electric current. In surgery, a fine heated platinum wire is used for cutting tissues much more efficiently than a knife. Thank you for listening and thank you for watching this presentation. I hope this would have helped you. There will be more such presentations in the upcoming days. So thanks again for watching.